So anyway, there'll be a link with the notes. Usually that'll be probably later in the evening. The video takes a little bit longer because I have to render the video, which takes a while, and then like upload it to YouTube. So that is generally be posted by the next day. Okay. We're going to be submitting a lot of assignments. A lot of these things are assignments that probably is easier to work out by hand than to try to type it out. I do a lot of math typesetting. I'm a big fan of LaTeX, so I get it. I love it, but it also takes a lot longer. And so a lot of the work I encourage you just to work it out on hand like you're turning it in on paper. And I'm happy to accept the hard copy. Some people like to turn in a hard copy. Most people prefer to submit them online because the deadline is always going to be by midnight or 11:59 on the due date. So a lot of times people want to push it out a little bit further and then submit it on Canvas. When you submit on Canvas, write it out by hand, but then scan it to PDF. You can use this. There's a scanner in the library. In Williston, there's a scanner.
We lost your audio.
Oh no! Really? Still?
It just came back when you realized it.
Okay.
It seems like you get a shorter somewhere.
Okay. I'm gonna leave this sitting here and maybe just let me know. Give a shout if it happens again. So in Williston, there's a copier in the 400 building that doubles as a scanner, and then some people like to use an app. Like Adobe Scan is good, Cam Scanner is good. There's probably 20 or 30 other apps out there. Here's the thing: I need something that I don't want image files. All right, don't send me a JPEG or a PNG or whatever. Also, don't make a PDF that looks like an image file that was just converted to PDF format. The problem with the image files is that they're too dark, and even if they show up well on the screen, they print out the page. It's just a page covered in toner, which is impossible to mark up. So I've got an example of a good scan and a bad scan. And I use the same image in the same app to create both of these PDFs, okay? I just put them through a different filter. I think I might have used Cam Scanner for both of them. But in one was just the regular photo. That looks like a photo. It shows up great on the screen, but it is really hard for me to use. I went to that and chose the black and white or something they call magic color or something. Anyway, I just chose a different filter and it shows up like that, and that's beautiful. It prints out nice and clear. So just make sure you got something that's a good, nice, high contrast thing that will print out nicely. If I get image files, or a PDF that looks like this, what I'll do is say, great, that counts, you did it, it's on time. I can't grade it until I get either a better scan or you hand me the hard copy. Questions so far?
Rachel.
Yeah.
Can you share the lecture notes as a OneNote file? I got the capability to draw in it.
You can. I've got the PDF here, and what I do is I print. I open the PDF and I print to OneNote because OneNote shows up as a printer. Is that something you're able to do? Yeah. So I just go in and I go into the table of contents, and I just see, oh, these are the pages I need, and I print those pages to OneNote, and that's how I get them on my OneNote. Yep.
Thanks.
Okay. Other questions so far? We still have some syllabus stuff to go through. Okay. I know the syllabus stuff is kind of boring. I'm going to, I think this part is important. I'm going to just explain how your work is evaluated. So I use the same grading rubric for all math courses, every level. It's just sort of what well executed means something different in this class than it does in pre-calc probably, right? But these are sort of the general criteria that I use for evaluating work. I look to see if it's well executed, whether it's well communicated, whether it is essentially correct. And so I've kind of described what each of these things means. And then based on those criteria, I just decide whether it's A-level work or B-level work or C-level work and on down. If it's A-level work, I don't really differentiate between mid-A and high A. I just call it all 100%. If it's B-level work, I call it all 87%. so it's kind of a rough scale. It is, so this scale here, it says goes down to 1. It is possible to get a 0, like if you don't do it, if it's blank, if the problem's missing, or if it looks like maybe you missed the boat entirely, like it's possible to get a 0. It's not common, like I'm not itching to give zeros, like make an honest attempt at a problem, and you'll probably get at least a 1, although I know that we're all aiming for something like on this side of the scale here. Once you get something back, when every time you get a graded assignment back, it'll have this grade cover sheet, so there'll be a little box for each problem. And next to the problem is a little number. This is the weight of the problem. I pretty much just stick to ×1 and ×2 problems. Like ×2 problems are just either longer or more involved or harder. So I'm going to go through this and just sort of make up a grade. So let's suppose somebody gets a grade sheet back and it looks like this. So what I do is, when each of these problems gets a numerical grade, and then it also indicates where it was on the communication. Communication is not a separate grade. Like how you did on communication is all rolled into that numerical, like how many points you got. I just indicate the communication on a given problem because that's often the criteria people have a harder time gauging where their work is at. So that's just for your information. But I take the numerical score, I multiply it by the weight. So this would be 5, 4, 2, 8, 10. I add up these points, and that'll give me the total number of grade points. So that's 10, 20, 29. Then I go over here to this chart, to this table, look up 29 grade points. Up here, that's at 88.86, and that's the percentage. Now, the next thing I'm going to do is just explain how I get the table. I'm not explaining this because I want you to explain to me how it works. I'm not going to test you on how the grading table works, but I just want to be transparent about how you get assigned a score, a grade. So if somebody, I'm just going to go back to this. If somebody got a 5 on each problem, you would expect to get 100% on that, right? So if somebody got a 5 on each problem, they would end up with 35 grade points, and that's why 35 grade points aligns with 100%. If somebody got a 4 on each problem, they should get 87%. And if somebody got a 4 on each problem on this grade sheet, that would add up to 28 grade points, and that's why 28 is aligned at 87%. So that's what I do first, is I just figure out, okay, what are the grade points for each of these benchmarks? A, B, C, D, and F. And then in between, so like I know 35 is at 100% and 28 is at 87%. So from here to here, it's linear. I just go down by the same amount. I say I got however many, 7 grade points, and I need to go from 87 to 87, from 100 to 87, and I just go by the same amount each step. So hopefully that makes sense, and it's not, just want it to be clear about how you get a grade on an assignment. Okay, I think that's the end of the syllabus stuff. Are there any questions before we get to the fun part? Okay. All right. Then let's go ahead and get started. We're starting in the first chapter, first section. A lot of like abstract mathematics courses start with a unit on set theory, and that's what we're doing. Sets form the foundation of really all math. So this is on page 5, I think. So a set is just a collection of objects. What is required for something to be a set is that if I name an object, you would be able to answer, yes, it's in the set, or no, it's not in the set. Like there's no ambiguity. Something is either in the set or it's not. Some common sets Here's like a little example for the margins. Like the set of integers is pretty common. There are some sets that are so common and frequently used in mathematics that they're given their own symbols. So this funky looking Z, this is the set of integers. This N is the natural numbers, which is the positive whole numbers. We'll work with these a lot when we do some number theory. The natural numbers are the same thing as the positive whole numbers or the positive integers. So another way to denote that is to say that the natural numbers is the same as Z plus. If you put a little superscript plus, it means just take the positive ones. We can list, we can denote a set by just listing the elements explicitly. So if I wanted the set of vowels, so it's a set, which means I'm going to put it in curly brackets. A, E, I, O, U. Somebody might look at this and say, what about Y? I would look at that and say, what about Y? Sometimes Y is a vowel, sometimes it's not. And because, so I sense a little ambiguity here now when I try to write out the list of vowels. If there's ambiguity about whether or not Y belongs in that set, we would say that maybe the set is not well defined. We always use curly braces to denote a set. When you put something in curly braces, it means the order doesn't matter, and sets are not ordered. Compare that to, like if we give coordinates of a point in the plane, like the point 24 is different than the point 42. We use parentheses when we do that, because when you use parentheses, that implies in mathematics that the order matters. And curly braces means that the order does not matter. And so we always use the curly braces for sets. The set of positive integers, we could start to list them out anyway. We can't list them all out. 1, 2, 3, 4, and then it keeps going. If we have an infinite set, a lot of the time we'll just list enough elements in order to establish the pattern, and then end with the little dot dot dot. The first n positive integers, now that's not an infinite set, that's finite. There's n integers in that set. But we're not being specific about what n is, so the first n positive integers, we'll use a similar notation, but we know where we're going to end at is at n. The set of perfect squares, that is an infinite set. So 1 squared, 2 squared is 4, 9, 16. And then I just want to establish the pattern. Maybe that's enough for somebody to look at and say, oh, they definitely mean squares. But I like to give some information, some specific information, like, oh yeah, I'm just taking squares there. It's still an infinite set. I'm still ending with the dot, dot, dot. So we can denote sets just by listing what's in there. It's also pretty common to use set builder notation, and you may have run into set builder notation. With set builder notation, again, we use the curly braces. And then we just use x, or it could be any variable, but we're just saying, here's an arbitrary element, we're going to call it x, and then we use either a colon or like a pipe, you know, like the vertical line. And then just say what has to be true in order for x to be in the set, just in English, right? So maybe this is a set. It's a set of students, and I'm just including students that are over 6 feet tall. So if we look at these two sets here that are written, one on the left and one on the right, the one on the right is really specific. It's objective, right? The student is over 6 feet tall. That's easy to determine. We have a way of determining if any given student belongs in that set. On the left, that's subjective, right? X is a tall student in this class. That's subjective. Anybody's a tall student to me. So I'm 5'3". So and somebody who's tall might have a different kind of metric. So we would say that this set right here on the left, this is not well defined. It's too subjective. I might build a different set from that criteria than somebody else. This one is on the right is well defined. Some notation. So we define, a set is really defined by the elements, by the objects it contains. So if something's in the set, we say it's an element of the set, and we use this kind of like sideways, weird looking E shape here. So if A is the element, is the set containing the elements 1, 2, 3, 4, we would say that 3 is an element of A. And if something's not in the set, like, for example, 5 is not in that set. So we just use the slash to negate it like we use to negate any symbol in mathematics. So 5, not in the set, not an element of A. So we use that weird looking E when we talk about individual elements and whether something is an element of the set. A subset of a set is a set itself that's just contained in some other set. So I don't know if it's possible to construct a sentence that uses the word set as often as that particular sentence, but so I have some set B, right? I'm gonna get kind of abstract here and just say here's my set B. Everything in that circle. If A is entirely contained, A has some elements of B, and it doesn't have anything outside of B. Everything in A is in B. That means that A is a subset of B. It's entirely contained in it. And we write here that A is a subset of B. If, let me do it, I'm going to draw another set, C. So here's C. C has a lot of stuff in common with B, but look, it also has some stuff that's not in B. C is not a subset of B because it has this stuff right here that's not contained in the B set. And if C is not a subset, we can indicate that by just, again, putting a little slash through it to negate the meaning. So here's a more concrete example. In example 1.3, we have some sets that they've just given to us by listing the elements. B is a big set, 1, 2, 3, 4. A contains the elements 1, 2, 3. Everything in A is in B. That means that A is a subset of B here. C overlaps with B, right? C contains 1, 2, and 5. C definitely overlaps with B because it contains 1 and 2, but it is not entirely contained in B because of this element right here. C contains the element 5. B does not contain that, and that means that C is not a subset of B. Two sets are equal if they contain precisely the same elements. Meaning, like we'd say that the set A is equal to the set B if everything in A is in B and everything in B is in A. Like, they overlap, they align, like, perfectly. A doesn't have anything that's not in B, B doesn't have anything that's not in A. So, saying A equals B is equivalent to making two containment statements. That A is contained in B and B is contained in A. A is a subset of B, B is a subset of A. If A is a subset of B but not exactly equal to B, like B has some stuff that is not in A, like B is legit actually a bigger set than A is, we might emphasize that it's a proper subset by getting rid of that line. Like, see, when we made these symbols, I put that little line over. It kind of looks like a less than or equal to, but like curved. That means it's a subset that could even be equal to the set itself. If I'm trying to emphasize that this is a proper subset, that it's contained in but not the same as the other set, I might just get rid of that little bar on the bottom, like it's a strictly less than, like strictly contained in this set. Most of the time, unless it's really important for context, I just kind of stick with this general subset notation. But the one without the horizontal bar at the bottom does have, I guess, a little bit more information about what's going on. Okay. So if we look at the first part of this definition that we just went over, we say A is equal to B if X is an element of A, if and only if X is an element of B, like they each contain each other. That definition is useful. That way of thinking about sets being equal is useful if we're going to show that two sets are equal. And we will a few times probably in this class. If we want to prove that two sets are equal, we basically have to do two things. We could break it down to two smaller problems. I'm going to prove that A is contained in B, and then I'm going to turn around and prove that B is contained in A. And if I've done that, then their powers combined means that the two sets have to be exactly equal to each other. And then another quick remark, I think I mentioned this earlier, but a set is defined just by what it contains. Order doesn't matter. Also, there are no repeats. Like the set 1, 2, 3. So here's a set containing the integers 1, 2, and 3. That's the same as the set containing the integers 3, 2, 1. It's the same as the set containing the integers 1, 2, 2, 3. Something's either in a set or it's not. It's not super extra doubly in the set. There's no reason to write the element 2 twice. In fact, that'd probably be considered bad form. If I were to count the number of elements in each of these sets, they each have 3 elements. And when you look at the last one, it's like trying to make it look like there are 4 elements. But 2 can only be in there once, right? It's like a binary state. It's a Boolean state. Some important sets. The empty set, the set with absolutely nothing in it, is we denote with a little circle through a slash in it, or sometimes it's just empty set of brackets. It really depends on the writer. You'll see me use the first notation more than the second. And then the universal set is everything. So those are the two extremes. We got the set with nothing in it, and then we have the set with everything in it. And now the universal set, what's in that really depends on context. Like if we're doing number theory, the universal set is the positive integers, like the natural numbers. If we're doing calculus, the set is usually all real numbers, or we might even just be talking about all real valued functions even. So we get a lot from context to determine what the universal set is. The size of a set is just how many elements. That's also called its cardinality. And we denote the size by putting a little absolute value around the set itself. We often use, like if I'm going to label a set, like we had those really special sets, right? We had like the integers with the weird z and the natural numbers with the weird n. But often we'll just use like capital letters, like capital A, capital B, capital C to denote a set. Just label a given set. And we just put absolute values around it to denote its size. So A is a set itself. Absolute A is the number of elements in A. How many things are in the empty set? It's not really a trick question. It's probably what you think the answer is. Go ahead and feel free to turn your mics on.
I'll take a 0 for 400.
Yeah, 0. Yep. You should have taken it for 1,000. Yeah, that's what defines the empty set. There's nothing in it, so its size is 0. How about this next set? How many elements? What's its cardinality?
1.
Nope.
Or no, that's 4.
That's 4.
Sorry.
Yeah. There's one set in the
Brackets don't
absolute.
count as an element,
Yeah.
right?
What's that?
The brackets don't count as an element, right?
Right. So this is the size of the set itself, which just means how many elements, not how many sets have we listed in there. That's a good question. And actually, there's a little bit of nuance there when we get to talk about the power set of a set. So here's a couple things to observe. Every set is a subset of the universal set. Everything belongs in its universe. That kind of makes sense. And the empty set is a subset of every set. Now, what that means is, if we go back and look at the definition of subset, I guess, if the empty set is a subset of every set, that would say that everything that's in the empty set is in, the set A or something, right? So let's say if some set A, that means that the empty set is a subset of A. It's not an element of A, by the way, because the empty set is a set. It's not an individual item. But it's not that, people have a hard time with that because there's nothing in the empty set to say is also an A. But I'm going to turn it around and say that you cannot find me an element of the empty set that's not also an A. So it's something we would call kind of vacuously true. Are we having fun yet? Lots? Don't all rush to answer that question.
It's interesting.
Yeah. Before we do the next section, I'm going to go off on a little tangent here with a kind of a paradox, which really troubled mathematicians for a long time. But there is a village. Here's the paradox, which comes in the form of a story, as most paradoxes do. There's a village, and in this village, the barber shaves everybody, every man that does not shave himself. And then the question is, who shaves the barber? Because if the barber shaves himself, then that means the person shaves himself, right? If the barber shaves every person that does not shave himself, like who could possibly shave the barber? Nobody, but the barber shaves everyone that doesn't shave himself. Like when you assume each possibility, it leads you to conclude the other one. It's like an infinite loop, right? And it makes brains explode and really rocked the world of mathematics for a long time. And the question like that is kind of what led to a really systematic view of set theory. What led to people developing a really rigorous approach to sets. All right, let's talk about set operations. The intersection of two sets. So right now, we're going to say the beginning in this definition says, for two sets A and B, I'm going to add to that preamble, for two sets A and B in the same universe. So they exist in the same context, in that same universal set. They exist in the same universe. The intersection of two sets is just the set where they overlap. It's all the stuff they have in common. In set builder notation, we would say that A intersect B is the set of all X such that X is in A and X is in B. The use of that word "and" is really important there. We have some notation here. We denote the intersection with this upside down U. The union of two sets is all the stuff that's in either A or B. Like throw them all together and make one big set. And we use a big looking U kind of to denote a union. And notice the language we use in the definition. It's a set of all X such that X is in A or X is in B. And in mathematics, the word "or" always means "or both," unless they specify otherwise, okay? So the union includes the intersection. Let's perform some set operations. Here they've given us a couple of sets, A and B. We want to find A intersect B. So A intersect B and A union B, they are sets themselves, so when we find them, I'm going to open up with a set of curly braces. What elements do we include in the intersection?
One, 3, 5.
1, 3, and 5. Yeah. Good. Those are all the ones they have in common. What about in the union? Mm-hmm. I'm going to just ask you to turn on your mic. This is going to be something that we're all going to work on because it's hard. It's easy to just keep our mics off, especially like when I'm in the room with you, like because you're answering a question that I've asked. But I just want to make sure that we include the other site. So somebody said 1, 2, 3, 4, 5, 7, 9. Right, we're just taking them all together, putting them in the same set. 1, 3, and 5 are in both sets, right? We listed them in part A, but they only get listed once in the union. They're not like super extra in a set. Once I have it, I have it. I don't need to add it again. The set difference, or set minus, is the set of all elements that are in A but not in B. So like, notice this is not commutative. Like the union and the intersection are commutative. Like A intersect B is the same as B intersect A. It's just the stuff they have in common. But A set minus B means start with A and throw out anything in B. B set minus A means start with B and throw out anything that's in A. So those will give you different sets. So it's not a commutative operation. The symmetric difference between two sets, and we use that little triangle symbol for it, is the union of the two set differences. So it's A set minus B unioned with B set minus A. That's sort of how we define it in set theory, but really you could think of it as the exclusive OR of two sets. Means you're in A or in B, but not both. So A set minus B. Here's another example. They've given us a couple sets. A set minus B. What do we include with this one?
1, 7.
1, 7. Anything else? I don't think so. Because 2, 4, and 6 are in B. Yeah, good. How about B set minus A?
3, 5.
3 and 5. Great, so those are all the things that are in B but not in A. Now the symmetric difference, I'm just going to throw these together. So 1, 7, 3, 5. Right, this is taking A set minus B, unioned with B set minus A. Questions so far? How are we doing in Williston?
Good.
Good. Okay. All right, let's keep going then. A couple more special types of sets that we can form. So let's suppose that we have a set A contained in its universe, its universal set. The complement of a set is all the things not in A. So you can't really define a complement without knowing what the universal set is, because you start with the universe and just throw out A. Like it's everything that's in the universe but not in your set. And then the next special set is the power set. Now, the power set is a set of sets. It is, I take a set and I look at all the subsets I could form in that set, and I put those in a set. So like the elements of a power set are sets themselves. It's, I guess, a little bit meta, but there are instances where the power set that we could kind of contextualize what it means. But the power set of A, like if we just kind of write out some, subsets here. So the power set of A, I think I need more space than I've given up there, so I'm gonna start fresh here. The power set is a set. So I'm starting with an open curly brace. What are some subsets of A?
0.
You mean the empty set?
The empty set, rather.
Yep. Good. Because that is a subset of every set.
That's supposed to be B, A?
No, it's P. It's like a weird looking P for power set. Some you can just write a regular P, but there's like a kind of. Oh, yeah. It's like a kind of an almost scripty looking P rather. What's another subset? We got one.
A set of each number. Yeah, a set of
We'll
one.
do.
Oh, the set of 1, the set of 2. And notice here, I'm not writing 1, 2, and 3. It's the set containing 1, the set containing 2, the set containing 3. I heard somebody in Williston say 1, 2. So the set containing 1, 2. One, 3. Two, 3. Yeah, the whole set itself, right? A is contained in itself, so I get to include the whole set. So, and then I close it with the curly braces. The power set is a set. Its elements are sets. So I'm gonna just emphasize some of the notation here, which really I think gets driven home when we talk about power sets. So the reason, I'm just gonna pick on, say, this one right here. Okay, there's the set 1, 3, that's a subset of A. So we would write, we already know this, that the set 1, 3 is a subset of A. That's why it ended up in the power set. But it's an element of the power set of A. So the fact that this is a subset of A, that's what means, that is equivalent to the fact that the set containing 1 and 3 is an element of the power set of A. Now, when we were listing these subsets, we got to 1, 2, 3, and I said, okay, and that's it. Like, I was really confident at that point. We had listed all the possible subsets of A. 1, 2, 3, 4, 5. The reason I was so confident is because we had gotten to 8 different subsets. I knew there was going to be 8 different subsets of A. A had 3 elements, and it is a fact that if A is a finite set with n elements, then there will be 2 to the n subsets. So 2 cubed is 8. I knew there would be 8 subsets of A, which means there ought to be 8 elements in the power set. The reason that there are 8, we'll actually probably talk more about this when we do some combinatorics, but when I form a subset, right, I'm just going to kind of do this off to the side. This doesn't take much room, but there's 3 elements of A. When I'm looking to form subsets, I'm basically just making a sequence of 3 choices. The first choice is, do I include 1 or not? The second choice is, do I include 2 or not? And the third choice is, do I include 3 or not? So I'm going to make a little space for each of these. It's a sequence of choices. Do I include 1 or not? How many choices do I have? Like, what are my options? How many options do I have? When I talk about the element 1.
2 choices.
Yeah.
Either include it or not.
Yeah, like I'm either going to include it or not. That's 2 choices. Then I move on. Do I include 2 or not? That's 2 choices. Do I include 3 or not? That's 2 choices. When you make a sequence of choices like this, the total number of choices that you have to make, you get by multiplying it. We call it the multiplication counting rule. We're going to look at that when we do some more combinatorics. But this is why there are 2 to the n subsets of any set with n elements. In some textbooks, we denote, and most textbooks do, denote the power set as P of A, like we're doing here. But some people will write it as 2 to the A, like that itself, instead of P of A. And the reason they do that is because of the rule that there are 2 to the n subsets in any set. I find that notationally confusing, like it looks like a weird type of operation, but there you have it. And I don't think it's, I don't think it's super common for people to do that. One last set operation that I want to go over today is the Cartesian product of two sets. So, when we formed a union or an intersection, those were just like elements of sets. They were sets in the same universal set. So A union B or A intersect B, they formed new sets, right? Or A set minus B, but they were still sets in the same universe, right? They still existed in the same universal set, or the complement of A or something. Now the Cartesian product gives us a new type of set. And the Cartesian product of two sets, I have to start with two sets. Their Cartesian product is a set of ordered pairs. So suppose I have the sets 1, 2, 3 is A and B is RS. The elements of A cross B, or the Cartesian product of A and B, I'm going to just form ordered pairs. It is a set, so I'm opening with curly braces. And the order here matters when I'm talking about A cross B, because it is this type of ordered pair, A, B, where the first element's in A and the second element is in B. They're ordered pairs. The order matters. So, for example, 1R is one of those ordered pairs, but R1 is not. R1 would be in B cross A. They're different sets. The order matters. And then, so there's one with R, but I could also pick 1 and S. There's another ordered pair. What else? Two and R, 2 and S. Mm-hmm. So the Cartesian product is a set, so it's important that I use curly braces in them, and it doesn't matter the order in which I list those ordered pairs, but the ordered pair themselves are ordered. Like, it's important that I use parentheses because that's what makes it ordered. That's how I let the reader know that this is an ordered pair. And it's important that I'm putting an element of A followed by an element of B. How many ordered pairs did we end up with? Yeah, so is there any pattern? How can I tell how big the Cartesian product is going to be using the sizes of the two sets?
The cardinality of the two sets multiplied.
Mm-hmm. And we could use that same multiplication counting principle. With the first element of the ordered pair, I have 3 choices because there's 3 elements of A, and the second element of the ordered pair, I have 2 choices because there's 2 elements of B. Questions? Okay. I think what I'll do is leave it there because we're not going to be able to make much progress through the next section in the few minutes that we have left. So these practice exercises, these problems are in the practice exercises document I handed out. Probably I would adjust this to 1 through 8. I think we might have to wait and do the last 3 after we cover the next section. Reach out if you have questions, please, between now and Wednesday. Take time to read the syllabus through carefully. Take time to read through the academic integrity standards, and then just log into Canvas and sign that contract. Let me know if you have any questions. Wednesday, I'm going to teach from Williston. So you folks, when you arrive here, just kind of go and sign on and join the Zoom conference. If you have trouble connecting, To the Zoomer, if you have any trouble in this room on Wednesdays when I'm not here, you can text me. My cell number's on the syllabus. Also, there's like a number on that binder that's up there, or you could walk down the hall to IT and somebody could help you too. Thanks, everybody.